Hello to all of you. First of all, it's really something new for me. Last year I gave 4 talks at the CppCon, but all of them online. It was 10 p.m. in Germany. It was totally dark and I spoke to hundreds of people. This was crazy, honestly. This was totally difficult to motivate yourself. I'm used to talk online. I'm a C++ teacher, I'm a Python teacher since around 24, and I did a lot of online stuff. But presentations are really bad online, honestly. So a few words about me. My name is Grimm. I'm only the essential facts. I give classes since 22, 24. I don't know it so exactly anymore. I started essentially with Python, with C++, and with our commercial product. My first online seminars, you may not believe it, were around 28. This was terrible experience, but now it's really, really fine. Okay, since 2016, I'm independent C++ in Python trainer. This is all you should know about me, and now let's talk about C++. In particular, I want to talk about the standard library containers. This is not rocket science, but I think this is stuff you should know to call yourself a professional software developer. Okay, this is the idea. I, of course, start general. Then I talk about these 3 kinds of containers we have in the library, in the standard template library. Sequence containers, associative containers, and since 11, unordered associative containers. And then I talk about something you may be a little bit bewildered, about your best friends. So what you should use, because we have more than one of them. Then I give you a guide, which container you should use or which you should avoid. And the main reason, of course, is in C++, for performance reasons. Okay, let's start general. This is totally general. You know what the STL is? Generic containers, generic algorithms. And how they come together? With iterators. Because the iterators, let me put it differently, the algorithms act or operate on ranges, and the ranges are defined by iterators, begin and iterator. This is a classical view. And sometimes you can adapt a little bit the algorithms by using callables. Here lambdas come nice into play. Once more, the general picture. Now we dive more into the direction of the containers. And this is what we have. When you count, you will end with 13 containers. I intentionally forgot here one, which is string, which should also be considered as a container. So we have 5 sequence containers. We have std array and std forward list since C++ 11, and since the beginning we have vector, deck, and list. Okay, sequence container. They give you the illusion that you can jump from one element to the other. This is why they call sequence container. And then we have associative container. They provide an association between a key and a value. And we have them in 2 ways. We have them ordered since 98 and unordered since 11. Okay. This is the big picture. And you know what? When I now would explain for each container what's its interface, this would be terrible. I have to explain 20 functions or member functions for 13 containers, and now you can calculate how many functions we would have. Therefore, it's extremely easy. They provide a common interface. This is the reason why they call it generic. And now I talk about the common interface, so what all containers provide. But as an example, I use here std vector. So instead of std vector, you can also now use std string, std unordered map, or what else. But I use std vector. So the container have a type parameter. You see it here, type name t, and an allocator. The allocator is defaulted. You will not see it. You will see it when you use CPP inside. You throw it inside, and then you see what the default parameter is. But it has an allocator. This holds for all containers. There's an allocator, which is an allocator for the elements, because they allocate memory. They support the same basic functionality, and this is the first very interesting point. They provide value semantic, not reference semantic. By the way, I totally look into the slide. They provide value semantic, not reference semantic. What does it mean? When you put an element on a vector using pushback, the vector wants to own its data. It's copied inside because now the vector is the owner of this data, of this element. It is responsible for deleting this element. Therefore, the only stuff you have to do is to give this element a meaningful destructor, if necessary. So this is value semantic. The vectors want to own its stuff, values. There's one exception. We have two special containers, sequence containers, stood array and stood forward list. First of all, stood array allocates its memory locally, and you have to specify its size during compile time. You cannot change its size during runtime, such as from vector and all the other guys. This is special. And the second point, what is special, is a forward list. A forward list is an extremely strange container because, for example, it even don't know its size. It has strong limitations. It's a single linked list. I will talk a little bit more about it in a few minutes, but it's a strange container because it behaves differently. I don't like it, but this is the way it is. You already have experience with stood forward list, or because you said something? Okay, and as I mentioned it once more, there are people complaining about C++. Strings are so terrible in C++. They provide no nice interface. I say, yes, you're right, but there are 100 functions which we call algorithms, and you can use them to manipulate the string. Because you should regard in string as a vector of char. And now you have a big, big interface. And this is not intentionally. A string has by design the same interface such as a vector. Just compare it. This is intentionally. So there's a big interface for string, but a little bit special. Okay. And now I just say a little bit about this common stuff. Once more, when I'm done with this general stuff, I dive more into the details. So each vector has a constructor, a default constructor. Okay. It has a constructor taking a number, so you can create a vector of 5 ints. It has a constructor taking a range, denoted by a begin and an end iterator. So once more, this holds for all of these 13. I only use here a vector to make my point. It has a copy constructor since 98. And since 11, it has a move constructor. It has an instructor taking an initialize list. Once more, stood initialize list of int is the formal type in this case. And there's more to it. It has a destructor, of course. And this is something new. This is one of the less remarks I make about C++ 20. With C++ 98, you can say clear on a vector. But with C++ 20, we have this three functions, stood erase and stood erase if. Here you can directly erase an element from a vector. In this case, you erase all 5 values, not 5 values, all numbers 5. This is the right way to say it. Or in the second case, erase if. It requires a predicate. A predicate is a function which returns a Boolean, and here you see the typical predicate which I use here is a lambda. And therefore, all is removed which is greater than 3, greater equal 3. This is a 20 extension. This is a replacement for this ugly idiom you may know, this erase remove idiom, which we use to remove something out of a container. You couldn't do it directly in 20. What can you also do? You can ask if it's empty, you can ask for its size, and you can ask for its theoretical size. Most of the time, this max size is way bigger than your memory, but this is just a number. Furthermore, you can assign. You can copy assign, move assign, and a kind of an initial list assign. I don't know how to say to it, but essentially it's an initialize list. And of course, you can swap. You can do it directly on the container, or you can use these 3 functions to swap. And comparison. You see, this is boring, but essentially it's good why it's boring, because now you can remember it. This works for all containers. You can compare 2 containers using equal or non-equal. are two unordered maps equal or non-equal? But with the exception of the unordered maps, meaning sequence in the ordered associative container, you can also apply the remaining 4 ordering operations. Smaller, smaller equal, bigger, bigger equal. But of course, this does not work for an unordered map because there's no ordering defined on it. You can, you can guess it from its name. And how does it work? To compare two containers, they must have the same type. You can only compare a vector of an int with a vector of an int, but not with a vector of a double. Wrong type. Two containers are equal if they have the same elements in the same sequence. Of course, this is trivial. And the containers are compared lexicographically. Lexicographically means you start on the left side with the first element and you make your decision when you detect the first element which is different. And then you say smaller, equal, or what else. This means lexicographically. Okay, and then we are done with the common stuff. Of course, we have, since C++11, it's quite easy to iterate through a container. So you see, this is the common interface. You can iterate through all containers which are essentially sequences. You can use the initialize list, a C-array, a C++ string, a STL container, or even a C++20 range, which I only mentioned for completeness here. And when you take the element by reference, I don't know if you can see it, here's my reference, then you can modify it. Because when you use auto without a reference, it's a copy. But here's the reference, therefore you can modify it. And this is quite comfortable. Honestly, I give classes. People using 98 are often unable to iterate through a container. Was so difficult in the past, but now it's easy. Strange best for loop. Okay, this was the common stuff, how should I say it? The boring stuff. But anyway, it becomes more and more interesting. First of all, do we have questions? Okay, let me talk about all the sequence container. And now be aware, I could not make it more concise. This is an overview of all sequence container. And I classify them based on a few characteristics. I cannot do it better, sorry. So first of all, when you look at the size, the only one which has a static size, meaning you have to determine it at compile time, is std array. This is your decision table. I will make it way easier when we go to the best friends. This is your decision table for choose this or that container. Implementation. Std array is a local C array. Std vector is a dynamic C array. A DEC, this is a little bit of simplification, is a sequence of C arrays. A doubly linked list of C arrays. Std list is a doubly linked list of single nodes. And forward list is a single linked list of single nodes. Okay, this is about implementation. Then, this is the interesting stuff, random access. So random access is provided by array, vector, and DEC. But not by a list. Because when you think about it, I have a list, doubly linked list, I can only go forward and backward. I'm not in an arbitrary position. Therefore, you only have a forward and backward iterator, and with a forward list, only a forward iterator. And exactly this is the characteristic of the iterators you get when you ask for an iterator of this specific container. Therefore, a list gives you a forward-backward iterator. And DEC gives you a random access iterator. In vector, also a random access iterator, in 20 even a contiguous iterator. Okay, then is the question, for which data operations they are optimized for? Std vector is optimized for doing something at the end, or one means constant. Std DEC, similar, by the way, when I say O of 1, this does not mean it is so fast for the DEC as for the vector, it just means constant. Constant can be such or such amount of time. Std vector is std DEC for begin and end. The same holds for std list, and forward list only begin. So this is optimized for. And now comes one interesting point. Whom of you knows the function reserve on a vector? What does reserve do? It allocates more memory than it, no, this is wrong what I said, but you're right. It reserves memory, and if when the memory you want to reserve is bigger than its size, it over allocates. And this is like extremely good idea. Why? When you know that you want to have a vector with 1 million elements, and you call always push back and push one new unit, this is terribly slow. Because always a memory allocation would occur, and therefore it will become really, really slow. But what you should do, call at the beginning, reserve 1 million, and then each pushback just pushes the elements on the vector without memory allocation. Because the simple rule for performance is don't interact with hardware. And this is the only guy who provides this is std vector. And once more, only to remind you, also std string. Only to remind you, always when you say vector, just keep in mind also std string. Then we have two functions, string to fit. String to fit is non-binding. This means the compiler could ignore it, but it means essentially you reduce its capacity to its size. Capacity is the stuff you reserved with reserve. So it's over allocates, and then you say, I don't need this additional piece of memory here anymore. You say shrink to fit. And this works for a vector and a deck. For list and forward list, this is not necessary. When you remove a node, the node is removed. No things here to discuss. This is one point which is, for me, maybe the most important point in this slide. Iterator invalidation. What do I mean? When you have a vector, and you have an iterator pointing to the fifth element or something like that, and you do something with this vector, this iterator is invalid. Why? Because changing something in the vector could cause a reallocation. It would stay here. And this holds true for std vector and std deck, but not for list and forward list. When you remove an element from a list, a node in this case, or from a forward list, the iterators stay valid. This could be a use case for these guys. Strengths, weaknesses. I make it a little bit shorter. Okay, array, no memory allocation. Minimal memory requirements, the same requirements such as a C array. Std vector is the 95% solution. I will come to it later. Std deck is good when you do something at the begin or at the end. The same holds for the list. And for forward list, a forward list requires extremely less memory. It has an extremely simplified interface, but sometimes this is the right way to go. So this is the benefit of a forward list. It's extremely needs less memory. It's extremely cheap data structure. What are the weaknesses? Array, of course, no dynamic memory allocation. With a vector, when you insert something in an arbitrary position, this has a complexity O of n, which means linear. But don't make any assumption before you say, I will not use a vector because I want to do something in the middle. Measure first. Don't believe it. Because there are other things here, but this is a theoretical observation. Okay, std deck, insertion, deletion at arbitrary position, O of n, similar to a vector. And list and forward list, you have no random access. This is a really, really issue. No index operator, essentially. And now let me talk a few things about std array. Okay. It's a homogeneous container of fixed length. And for me, a std array is a combination of a C array with the interface of a std vector. It just comes together. And in particular, std array has one big benefit. It knows its length, in contrast to a C array. And this is often a reason for a lot of fun in the program. Okay. Array initialization is special because array is an aggregate, and here the aggregate initialization rules apply. Means here no elements are initialized. When you use empty curly braces, all elements are default initialized. This is, by the way, a C array also works, because under hood it's a wrapper around the C array. And last, when you only specify 5 elements, the first 5 element gets this value, and the second one are default initialized. The remaining one are default initialized. Stored vector, you see, it has a size and a capacity. Typically, a vector over-allocates by a factor 1.6. This is a typical what they do. And here you see the capacity is around 15, but the size only 10. U, homogeneous container of variable length, manages memory automatically, stores its element contiguously. This is extremely important because of performance reasons. I will show it to you later. Therefore, you have an index operator. And it over-allocates or reserves memory to get rid of expensive memory allocations. You can do something in the front and the back. Let's make it relatively fast. This is something which a few people don't know. You can access the element by the index operator, and here you are on your own. When you apply the wrong number, this is undefined behavior. But when you want to be sure that you don't make any mistake, you can apply the add operator. This add operator checks boundaries. You get in case of out of range exception. And of course, you can do pointer arithmetic. I don't like it. I don't know why I mentioned it here, but you can do it. Okay. Let me extremely fast. You can assign to it. You can insert something. Who knows what's the difference between insert and in place? Go on. Exactly. You only provide the arguments for the constructor of the elements, which should be the elements of the vector, and with insert you provide the elements. So theoretically, should be faster. Let me make this short, because I think here's the deck. This is simplification, a doubly linked list of series. The name deck comes from double-ended queue, and essentially it provides a similar interface such as a vector, but you can also do something on the front. Push front, pop front, in place front, essentially. Then we have the list, doubly linked list. This is extremely different data structure. You can access relatively fast something at the front and at the end. And it supports special member functions which are optimized for pointer operations or manipulations, such as split, merge, or something like that. And now to the last guy, and then we are done, and then I come to the associative container, which are a little bit more interesting. Forward list. It only grows in one direction. Once more, only use it when you know this is enough for you, because it has an extremely limited interface. It's a single linked list, similar to a stud list, but it's optimized for minimal memory requirements, but it even don't know its size. And you can only iterate in one direction. And to count how many elements you have to iterate through it and to count manually. So it's extremely limited. And now, first of all, any question? If not, I will come to the more interesting guys. Ordered associative containers. I do it for the ordered, the unordered, and then we come to the best friends. Ordered associative containers. And here's the first strange sentence. What is an ordered associative containers? You know how I explain it in my class? It's an analogous, oh sorry, I have problems to pronounce it right. Who can do it for me? Analogous, thanks a lot. Phonebook. What is a phonebook? Analog is, of course, something you have in your hand. You have a digital, but guys which are so old as me, no, we had in the past different ones. Okay, what is a phone book? A phone book is a sequence of key value pairs, right? And you use the key, the family name, to get the phone number. And this is a phone book. And you can hope for it that it is sorted. Imagine you would have the phone book of all people from this town, from Denver, and it would not be sorted. Therefore, it must be sorted. If not, you have an issue to find your phone number. So it's a phone book, and we have 4 versions of phone books in C++. The classical one is a stud map. But sometimes people want to have more than one phone number. A stationary and a mobile. Then you use a multi-map. You can have more than one key, more than one family name. And set and multi-set are restricted phone books. This phone book has no value associated. It can only give you the answer, does this guy have a phone or not? There's only the family name inside, but it's essentially a phone book, but without an associated phone number. So just phone books. And here is how the most common phone book signature looks like. This is stud map. It has a type, in this case it had types, key and value, of course, family name, phone number. It has a comparator, which is defaulted to std_less. This is a function object we have since C++98. It's similar to a lambda just. And it has, of course, an allocator. And here you see exactly what's inside the phone book. It's the allocator of std_pair const key value. So it's a sequence of pairs. Okay. And here's some very interesting observation. This is how a phone book looks like internally. It's a binary balanced search tree. Binary means each node has 2 childs at most. Balanced means the leaves are on the same level with, how should I say it? There could be one level between the leaves, but essentially on the same level. This is what it means. And here you see how I fill it with an initializer list of pairs. And now it's the interesting observation. And once more, it's ordered in ascending order because under hood std_less is used on the key. Wait a second. On the key, you see, compare std_less key. So key is the interesting part. Of course, your phone book is also sorted on keys, not on the phone numbers. You see? This is why I say it's a phone book. Okay, but here's the interesting part. When you now search for 8, you want to have the, for the number 8, the corresponding string. You start at the root and you say it's a 4. 8 is bigger than 4, therefore you go right. 8 is bigger than 6, therefore you go right. 8 is bigger than 7, therefore, oh, there's nothing left. There's no 8 inside. And this is an extremely important observation. When you have a big problem and you solve this problem by dividing it into smaller problems of the same size, such as here, I go either left or right, then the complexity of accessing something is logarithmic. This is an extremely simple observation. This is why quicksort is a logarithmic sorting operation. When you do something and you solve the thing by just dividing this thing and do it recursively on itself, you get automatically logarithmic complexity. Meaning, when this data structure becomes 1,000 times bigger, your access time becomes logarithmic times slower. This is totally important because I want to talk about your best friends on the end. And what I like here is, this is extremely easy to remember. You have only to think about how is this structure internally built. This is typically how it's structured. Okay, so the most popular one is the ordered associative container. It supports the index operator, meaning you can go ask for the 8 and you get back the string 8 if available. And here's something which often irritates people. The index operator, when you want to read something, you go inside. What would happen when you look inside? You see this? This picture with a phone book does not hold always 100% true. But anyway, what would happen when you go inside a phone book? You want to have the family name of Grimm, but Grimm is not inside the phone book. You would get an error, of course. But not in the case of the map. And this is what many people irritates. In the case of a map, a key value is created with the key which you ask for and value the default value. Meaning when you have a string, it's an empty string. And this is, so reading from a map is not a reading operation, it's a mutation. This is critical. And I don't know if I like this behavior or if I prefer more Python, which says, this is a key error exception. But anyway. This is how it is. And when you want to be sure, you can apply the same operator you know from vector, from array, and from string. And now you will get back an error, meaning exception, when the key is not available, in this case, out of range exception. Here you are on the safe side. And now to the more interesting guys, to unordered associative containers. They were added with C++11, and So what is an unordered associative container? It's a digital phone book. Why? In a digital phone book, you only ask with a family name, and you just get back the value, phone number. There's no ordering required because there's a search algorithm behind, probably. This is a digital phone book, but it's also a phone book because it's a sequence of key value pairs. And you use the key to get the value. And we have 4 kinds of phone books since 11. Unordered map is the classical phone book. Just a key value association, and there can only be one key. Unordered multi-map, as before, more than one key, identical key, is possible. And set and multiset, such as before, the value is missing. A phone book without a value, you just get the answer, this guy has a phone number or not. And because the unordered map for me is the most powerful data structure we have. I will come to it because it has an extremely interesting performance characteristic. And because it's so heavily used, it has totally different names. When you make Python, you just say dict or dictionary. This is exactly unordered map. This is a dict. Or you say sometimes also associative array. I like this term. Why? What is the key in a C array? When you have a C array, what is your key to get the value? Exactly. What type is it? A number at least 0. And how you can regard an unordered map is just an extension of a C array. Because not only you can use an int, you can use string or almost any arbitrary type. Okay. Or sometimes it's also called hash table. I will talk a little bit more about the implementation because it's quite interesting. And here's some interesting observation. The unordered associative container extend the interface of the ordered associative containers. What do I mean by that? An unordered map can do all stuff a map can do, but a little bit more. It supports the same interface, or as enriched interface. The same goes for unordered set versus set, unordered multiset versus multiset, and so on and so on. What is this? Do you have an idea why this is the case? Why does an unordered map support also the interface of a map? When you have data structure which have an extremely similar interface, this is most of the time not by accident. There was some thinking behind. Do you know which one? Let me give you a tip. This always works when you are in a C++ class. When you don't have an answer, just say performance. The reason is the following. When you have a map, and what I show you, and use a map to implement a phone book, and then you say, oh, it's too slow. You just switch from a map to an unordered map. It supports the same interface, and it becomes, with high probability, way, way faster. And this is the reason. You can replace these data structures because they support a similar interface. Okay. And when you look here, this is the Pandorzo map, the unordered map. It looks a little bit complicated. You see it, the template declaration. It has a key value, this is trivial, and it needs a hash, a function to determine the hash value from a key. I will talk about what a hash value is. And it needs an equal function, which is defaulted to equal on the key. So once more, what is key here is the key. The key counts, not the value. The value is just something beside. And of course, it has an allocator, such as before, but this is trivial. Okay. Now you see what is required to have an unordered map for a user-defined type. You would have to define, if it's not there, a hash function and an equal function. This is now I can use it. And when you go back, what would you have to define for a map? When you have a user-defined type, what must this user-defined type support to be usable? Sorry, it's a little bit too slow here. To be usable in a map as a key. What is required? Does any value work as a key, any type work as a key? Of course not. What is required? You need, have a look here. You need, this is a little bit terrible. Here we are. You need ordering, stood less key. Without ordering, you cannot build this tree because you have to sort this tree. And this is a requirement for a map. For a map once more, you need, I simplify a little bit, ordering. And for unordered map, you need a hash function and an equal function. So you see, different requirements. And now let me tell you a little bit more about the implementation of an unordered map. Here we are. This is how it looks like. I have an unordered map. Oh, damn, there's an error. It's not called unordered map. I fixed it in the wrong way, but you see it. But it seems not to be so a big issue. Okay, unordered map. How is the unordered map? How does it work? You have a key, such as Grimm, and its value, assume this is a phone number. You want to add it to this data structure. And now you make something with the key, only the key. Value, I don't care. With the key. What is happening in the first place is you apply the hash function on the key. The hash function takes this Grimm and makes a unique ID out of it. 43, for example. This is the first operation. In the second operation, on the left or on the right are buckets. For simplicity reasons, 10. And then you divide this 43 modulo number of buckets. Finally, Grimm goes with his value into the bucket 3, 43 modulo 10. This is how it works. Then you have Schmidt goes to 55, modulo 10 goes in the fifth bucket. And then you have Huber, 3, modulo 10, 3. Now Grimm and Huber are in the same bucket. Is this an issue? No. This is called a collision. In this algorithm can deal with that. And now when you think about it, the operation from the key to the bucket, determine the hash value and then modulo number of buckets, is a constant operation. But searching in the bucket is a linear operation. So your goal is to keep the buckets as empty as possible. Sorry, this is the wrong way to say it, but you know what I mean. Why do I explain you this stuff? Because an unordered map or all these unordered associative containers have one extremely important property. Which one? What did I say to you? What should I say when you don't have an answer? Performance. They have constant access time. What does it mean? When you have a phone book with 1 million or 1 billion elements or 10 elements, you will get the same answer. You will get the answer in the same time, independent of the size of the phone book. For a map, this does not hold. It becomes logarithmic slower. I explained you this with this tree, you know? This is unbelievable property. And now I explain you why this is the case it is. So, here are a few terms, only to sound smart. So we have a collision. More than one key is one bucket. This is by the reason why we need the equality function, because you have to decide which key it is. This is what I said. Then we have the term of capacity. This is the number of buckets. Then we have a load factor. And here comes the extremely interesting observation. When, in average, more than one key is in one bucket, new buckets are created. This is only default behavior. You can change it, but this is default behavior. Once more. When you have 1 million keys, you have typically more than 1 million buckets. Don't think about big memory allocation stuff. It's only a single linked list, typically. And this is what's happening. When you have 10 keys, 9, and you have 10 buckets, then you put a new element to your phone book. New buckets are created. And this process is called rehashing. And as always, similar to a vector, not only one new bucket is created, more than one, because memory allocation is expensive. This is similar to reserve for a vector. And here comes the extremely interesting observation. I don't know why. I have to say something interesting. With Windows, always the next power of 2 is created. So it goes from 1024 to 2048, and so on and so on. This is the way the number of buckets increase. And when you think about modular operations, it makes sense because half of it are still in the right bucket. And with Linux, I only observed GCC in Klang. They always go to the next prime number. This is, sometimes you see differences, and here it's one. Just try it out, you will see it. You can see the details in C++. I don't have an example here, it would go too far. But this is a totally interesting observation. And this is true since I teach C++ in this feature. Okay. First of all, I have to make one question for you. So we know when the number of keys increase or the number of pairs increase in my phone book, the number of buckets also increases. And this means when new buckets are created, the keys are distributed different buckets because modulo 10 is different to modulo 20. And this is an expensive operation. And to overcome this issue, there's a nice function in C++ which is called rehash. Therefore, you can say at the beginning, I have at least 1 million keys. Therefore, I should have at least 1 million buckets. Similar to reserve to address the capacity. And therefore, also building of an unordered map is probably faster than building of a map or filling of a map. I never tried it out, but it's my assumption. Because for map, there's no way you can improve this. Okay, but now I have one question. What is the natural hash function for int numbers? Imagine you would have a map which goes from int to string. What is the natural hash function for an int? And this is the function which is used in Python and also C++. What would you use as a hash function for an int? Each number must go to a unique number. So what do you use? No identity. Yeah. You see, it's fast. Nothing happens really. You can see it. They use identity. Okay. And now we come to the fun stuff. Once more, now I want to talk about your best friends. The best friends you may not know so far. Because so far we have 13 containers, and you may not know which one you want to use. Okay, let me start with the sequence containers. And here it's quite simple. I only mention it because I have to mention it when not someone would complain. You should not use a C array, you should array and should vector. And here's my point. In almost all cases, you are totally fine with an array and vector. I will show it to you out of performance reasons. And here's the simple idea. When the container size is known at compile time and small, use a std array. When it's not known at compile time or big, by the way, here I say big, above I said end. Not known at compile time or big, use std vector. Why must the size of an array be small?
Because it goes on a stack.
Exactly. And how big is a stack? 1 to 2 megabyte. A heap should be a little bit bigger. And therefore, when it becomes really big, you have an issue with the array. And therefore, this is a simple rule which you could apply. And I give you a few performance numbers, then you see these are your best friends. So to repeat, north is size, ultimate management memory applying RAI, has an add operator, and here's the key point. Our compute architectures are optimized for contiguous memory blocks. For reading of contiguous memory blocks, I just give you here one word. It's cache lines. Meaning when you read something from memory, you read not one thing, you read 64 byte. You read not one int, you read 16 int. Typically, you need the next int, but now it's in an extremely fast cache, and therefore you can access it extremely fast. And this effect is so important that even my consideration about list and forward list, forget it. Don't make assumption, even when you put something inside a vector. I'm not sure if this is slower, because cache lines effect are really, really hard. And they may become even more harder because memory becomes, the gap between memory and CPU becomes bigger and bigger each year. Don't make here any assumption. And here is a few numbers I want to show you. But this is on my PC. I have it also in my slides, but here is a few numbers. Here is an extremely simple performance test. And here's what I do. I have different containers. I don't use a vector because a vector cannot hold how many elements? Here we are, 100 million elements. So what I want to do is the following. I want to add together all elements of different vectors. I go from begin to end, and I say the initial value is 0. I just sum them up. This is what std accumulate does. Just don't think about implementation, just think about it sums up all values from t begin until t end. And what I now create is different containers with 100 million arbitrary elements. And I just sum them together. I use a little bit of randomness here. You see, I just allocate in memory a vector of 100 elements, and I push them here back, using a little bit of randomness. And now I apply this function sum up for a vector, for a deck, for a list, and a forward list. And here's what I do. I measure the time here, and I measure the time afterwards. Then I display, to be sure, the final result, which should in each case be identical. And I display also how long it took. So far, good? One question only for you. I want to be sure that you know your stuff. Why put I here an arbitrary scope? I do it quite often, in particular when I do concurrency. Why did I put here 2 additional curly braces? Exactly to apply RAII. Because now the lifetime of my VEC will end, and therefore the stuff is removed. Okay, now let me run this example. Any question about this example? So let me show you the number. So once more, I apply on each container the same algorithm. The difference can only be the memory layout. There's no other thing here different, you see? And now these cache line effects or these continuous memory block effects kick in. And here are the numbers. No, not the numbers. At first I have to execute it. But anyway, what was the name of the program? Memory access. For some strange reason, autocomplete does not work on my PC. By the way, is it big enough? I don't know. By the way, I don't care about the. Damn, is this langsam, slow. Sorry, this was a German word. I don't know what's happening now. But I can give you, now we are done. Only for gut feeling, std vector is around 30 times faster than a std forward list. You see, all give you back the same result, but here you see the numbers. In the resolution of numbers is seconds. You see 0.4 around for vector and 1.9 for forward list. DAG is not so bad, but list and forward list are extremely bad. Because you know what happens? You have a list, one node, here one node. You read this element, and you read the entire stuff afterwards, which is stored in internal cache, and then you want to have this element, and it says, oh, this is not in my cache, I have to go once more to this extremely slow memory. This is what's happening here. You have a lot of cache misses, or sometimes also called the cache is cold. You see? And when you want to have more, I don't care if it's 20 times slower, 15 times slower, Linux or Linux, this is Windows. Let me go once more back here. Let me show all 7 minutes, I'm extremely good. Here are the performance numbers. Here, this green is let me put it so. Damn, is this slow here? Damn, I don't know why. Anyway, here are the performance numbers. You see, less than 0.1 seconds for a vector or a vector. The green line is Windows, the other line is Linux. Don't compare the numbers, these are different PCs, only to get a gut feeling. And with stack, it's not so bad, but with a list and a forward list, it becomes really, really slow. I showed you the numbers live, and these are numbers from a different PC, but only to get a gut feeling. So what do you learn so far? Your best friends are vector or array. And now the next point. Should I use a map or should I use an unordered map? Which kind of phone book do I want to have? And here's the next performance test. This was a little bit more complicated, but anyway, let me show it to you. I will show it to you live, and then I show it to you the numbers on the slides. Sorry. You see, I'm a Linux guy. It's cat, or what is it? Cat, I think, or more. What is on Windows? Show a file. Sorry? We will see it in a few seconds. When it works, it works. If not, I'll try something different out. I don't know it. This is a big, big phone book. It has 90,000 entries. By the way, I created the phone numbers. I found in Scandinavia 90,000 family names, and I created a phone book out of it. And you see, who said to me that I should use this example here, this tool? It takes a few seconds. And here's my performance test. I create an arbitrary permutation of all family names, and I want to read each entry in this phone book. I start with 90,000 and then I end with 90 million. Do you know why I ended with 90 millions? My PC crashed. Can I stop this garbage here? Oh. Control C, does it work on Windows? Ah, I'm happy. I'm so glad this is my small phone book, only 90,000 entry. My big one has 90 millions, and to give you an idea, this is enough for Germany, so it's really big. And here's my performance test. First, let me show you my idea. First of all, I make the following here. I say using map stud map. This is my phone book in which I put all the key value pairs. And then, you know what? Unordered map supports the interface of a map. Therefore, I say in the next iteration, using map equals stud unordered map. And this makes it extremely convenient for me to just switch the implementation of the phone book. So what I did here, forget about it. I opened the file, I read it, I did a little bit of regex, and here's the essential line. Here. This is the essential line. Here, where is it? Here. Names is an arbitrary permutation of all family names. And here I iterate through all family names. I want to have the phone number. And this is my performance test. I do it for 90,000 and end with 90 million. And now I want to know how fast is a map compared to an unordered map. Because the map must become logarithmic slower, but not an unordered map. Okay, here are the numbers only on Linux, on Windows. Here are the numbers, and then I show you on the slide, and then I'm done with my presentation. Let me see. Here's the numbers for Telebook. I should use shorter names. So essentially, these are not 90,000. You see 88,000, but similar to that. And now you see, okay, it took 0.7 seconds. When I now use the unordered map here, we hope that it is faster. I already compiled it. As always, when I do a performance test with maximum optimization, and you see it's around, who can, 7 times fast, is this right? But anyway, let me provide you the numbers. Here are the numbers. This will take a few seconds, I don't know why. This seems to be power related or HDMI related. Here are the numbers. This is what you know. This are the relative numbers. When I have 90,000 entries, these are the numbers, by the way, on Linux. What we saw was Windows. Windows was a bit different. When I have 90,000 entries, unordered map is 3 times faster than a map. When I go to 90 million entries here, I don't have this data anymore. I removed it. This was too much stuff on my hard disk. When I go to 90 million entries, unordered map is around 8 times faster than a map. And this goes further. And here are the absolute numbers. Map and unordered map. And here you can see something interestingly. For example, when I ask for 90 million entries, it is around 5 minutes. But with the unordered map, 40 seconds. You see, this is a big difference regarding performance. And here's the second, I have 9 seconds left, I will match. And here's the second totally important observation. When you go from 8 million I simplify, from 9 million to 90 million, it becomes 10 times time 1.6 slower because it's logarithmic. But here, it's almost linear, you see? When the data structure becomes 10 times bigger, the access time becomes 10 times slower. It's not exactly 10 times, but something like 11 or something like that. But here you see it. The access time is independent of the size. And this is an extremely important observation. You have an extreme big phone book, you get the answer at the same time. This is what the unordered map provides you. And therefore, what is your best friend regarding associative containers? Sorry? Unordered map, exactly. Only when you need a guarantee that the keys are sorted, then you can think about it, or you can do something differently. My last slide, first of all, I'm almost done. I talked about the general stuff, the sequence containers. You were maybe a little bit bored because it was not so challenging or interesting, but the ordered and the unordered stuff should be really, really interesting. And now you know what are your best friends, meaning this is your choice before you do anything, use this guys. And only when you have concerns, try the other out, but not without measurement. And when you want to know more, I have written a book about the standard library, only a small one. I have written a lot of posts on my blog, Modernist C++. Don't be irritated. It's intentionally called Modernist because I'm German. Therefore, my company is also called Modernist C++, and you can have training or mentoring. Now I'm done. Thanks. No question?
Yeah, we have one online question.
Okay,
by Andy Stern. Do you have an estimate of how many elements would be better storing in a
little bit louder or close the door. This is a little bit difficult for me.
Do you have an estimate of how many elements would be better storing in a nested vector and searching with a binary search versus using a map or unordered map to cache locally?
I don't get it. Do you have? Let me
estimate of how many elements would be better storing in a nested vector and searching with binary search versus using a map or unordered map to do?
This is a good point. A map has a similar performance characteristics, such as using a vector and using this way is called or you go in the middle and you go left or right. Once more, when you have a vector, good point. When you have a vector and you want to search for an element, first of all, what you should do, you should sort it. Then you go in the middle and then you go left or right. This is, from a theoretical perspective, as good as using a map because you go in the tree, but a vector has a memory layout of meaningful. Therefore, a vector will become way, way faster. And this is the reason why we will get, I'm not 100% sure, with C++20, a flat map. This means a tree which you hammer until it's flat, and then you have a sequence of key value pairs, but in a vector. And this is extremely expensive to build, but extremely fast to read. But I'm not sure if you will get it with C++23. I assume yes, but I'm not 100% sure. I hope this was the question. Okay, we are done.